even though we've been working with derivatives for a while and actually looked at a few intervals, we now want to take a step back and take a look at a few more limits. Um, Try to do some limits that previously we would not have been able to do, and just to show you an example of the type of limit that we're now going to be able to work. This one, notice that if you simply plug in the 1 for x, you get a 1 squared minus 1 on top, a 1 squared minus a 1 on the bottom. We end up with a 0 over 0. Now, you have learned previously, and it's probably been pounded into your head many, many times, that you can't divide by 0. So if you have something like a 5 over 0, that's undefined. If you're having a negative 3 over 0 or something like that, that's undefined. But we're not evaluating a function, we're doing a limit. And with limits, you can plug values in. If you had a limit, like the limit as x approaches 2 of x squared plus 3, then in that case, since that's a polynomial, in that case, it's perfectly legitimate to say, well, that's a 2 squared plus a 3, which is a 4 plus a 3, which is a 7. All right, that's a situation where you're totally allowed just to plug in. But when it comes to limits, if you plug the number in and you get what I've sort of have come to call a red flag, you get something weird like this, then that means that just plugging the number in was not the right way to go. Again, if this was a function, if this was f of x equal x squared minus 1 over x squared minus x, all right? And again, let me write this out. If you had f of x being x squared minus 1 over x squared minus x, and you said, what is f of 1? If that was the question, the answer would be that at this value, at this 1, this particular function does not exist. The function is undefined at that value. 1 is not in the domain. And 1 is not an element of the domain of that function. But again, we're not looking at a function looking to evaluate it. That's not what's happening. We're looking at a limit. And if you remember, with limits, the one thing that we really don't care about, even though we actually evaluate it that way on a regular basis, but in reality, the one thing we don't care about is what this is equal to at 1. We only care about what's happening as you approach 1. And in this case, approach it from both sides. So the 0 over 0 is going to be the first of actually several of what is commonly called indeterminate forms. All right. That basically means that if you plug and chug, as it's sometimes called, if you just put the number in and you get something like this, that literally means that the limit could be just about anything. The limit could be just about anything. Now, one thing, before we get into this new rule, one thing I will mention that you should remember is that with limits, you're always allowed to do algebra. As long as you're performing correct algebraic manipulation, you really can't go wrong. So in this particular case, if I wanted to look at this limit, what I could possibly attempt to do is a little bit of factorization. All right, after factoring, the x minus 1 factor will disappear. And again, since I have done legitimate algebra, I can try once again to plug in the 1. And this time when I do it, I get an actual legitimate numerical value. All right, so I wanted to, from the very beginning, before we get into this new rule, point out that algebra is still allowed. You still are totally allowed to do algebraic manipulation. But in situations, I picked this problem on purpose because the algebra would work. But there will be situations where there is no algebra that would help you. If you want to take the limit as x approaches 1 of natural log of x over x minus 1, all right? Well, one thing you need to remember is that with your natural log function, you got to remember what that function looks like. Natural log is the inverse of the e to the x. And what happens is the natural log actually hits the x-axis, all right here at 1. All right, 1 is the x-intercept. So that means with this one, when you just plug and chug, again, as I like to call it, plug a 1 in here, plug a 1 in down there, you get the 0 over 0 again. You get the same indeterminate that we had last time, but this time there's no factoring, there's no algebra that can help you. And again, this literally means that the limit could be absolutely anything. It could be any number you can think of. It could be positive infinity. It can be negative infinity. This literally means it can be anything. All right. So one thing I want to do, I don't want to put it off. I want you to have a completely thorough list, a complete list of the indeterminate forms. All right. And with these indeterminate forms, we're going to use something called L'Hopital's rule. And L'Hopital was actually a French nobleman, and his name is on this rule or on this theorem, but this theorem was actually discovered by John Bernoulli. And if I remember correctly, the way it worked is L'Hopital wanted his name to be famous, so he purchased this. He purchased the rights to put his name on this from Bernoulli, because at one point in time, that was seen as a perfectly okay thing to do. All right, so anyway, with L'Hopital's rule, your indeterminate forms are on this list. And let me point out that anything that's not on this list is not an indeterminate form. It's not indeterminate just because it looks confusing or difficult to understand, right? Indeterminate is exclusively what's on this list. So just to be really clear, 0 over 0, if you plug and chug, if you plug into a limit, the limit value, and you get 0 over 0, that's an indeterminate form. An infinity over an infinity, and with the plus or minus here, what I'm trying to say is it could be a positive infinity over a positive over a negative over a positive, or a negative over a negative. But 0 over 0 is indeterminate. One infinity over another is indeterminate. 0 times an infinity is indeterminate. Infinity minus an infinity is indeterminate. 0 to the 0 is indeterminate. Infinity to the 0 is indeterminate. And 1 to the infinity is indeterminate. Okay, those are indeterminates. And again, it's not on this list, it's not one of your indeterminates. All right. So let's take this list, had a chance to look at it, and let's work a few limits. All right. Start off with the one that I had. Let's say I had the limit as x approaches 1 of x squared minus 1 over x squared minus x. We've already worked it out algebraically. Now let me show you what L'Hopital says. L'Hopital's rule says that if you have a limit that is in the indeterminate form of either 0 over 0, which is what we have this one, that's what we have here, or one of the infinities over a different infinity, or the same infinity, like this is the infinity over infinity scenario, then L'Hopital's rule says that I can take the derivative of the numerator and the derivative of the denominator and evaluate the limit at that same number and get the same result as I would have had with the original limit. Now, be aware that, again, L'Hopital's rule is only going to work once you have things in a fraction form, a quotient form. It has to be in a fraction form. It has to be in an indeterminate form of either 0 over 0 or one infinity over another infinity. But if I have one of those forms, I can differentiate and evaluate my limit that way. For clarity, let me say you will not use the quotient rule. That's not what L'Hopital's rule says. L'Hopital's rule says that I can take the limit as x approaches 1 of a 2x minus 0, which is the derivative of the top, over a 2x minus a 1, and it will be the same. All right, again, notice that I did not use a quotient rule. I just took the derivative of the top as it was written, took the derivative of the bottom as written. Let me clean up a little bit. The 2x minus 0 is a 2x, and a 2x minus 1 is a 2x minus 1. And again, what L'Hopital's rule is saying is I can simply now plug in a 1 and you'll notice I get the same outcome as what I had before. So again, L'Hopital's rule doesn't say, hey, don't do algebra anymore. There will be instances where you need to. L'Hopital's rule will allow you to evaluate things that, again, maybe the algebra would not have helped you with, like that second example that I had. If I have the limit as x approaches 1 of natural log x over x minus 1, with the problem on top, yes, I could have done some algebra. I did in a previous example do some algebra and get it figured out that way, but you don't have to. In the second example, there really isn't anything you're going to be able to do in the way of algebra to help you. Again, I will verify that I should be using L'Hopital. And by that, I mean plug in a 1 here, plug in a 1 here, and I will get my 0 over 0. And that says it's okay to use L'Hopital. And I will take the derivative of the top, which is a 1 over x, take the derivative of the bottom, which is a 1, all right? And let me sort of go ahead and introduce a notation, something you will not see used all the time, but something that can be used is above the equals to, they will on occasion put a small h, like maybe I could have done that up here too. And that means that for this step, L'Hopital's rule was used. So if you see that in a solutions guide, if you see that in somebody's work, that's what it means, is L'Hopital was used. Again, I will come in here, do a little bit of algebraic simplification. Now I can plug the number directly in, and I will have my limit. All right. Notice I didn't write the h again because I didn't use L'Hopital's again. So you may be wondering, can L'Hopital's rule be used more than once? Is that possible? Is that allowed? And the answer is yes. That is not at all out of the question for L'Hopital's rule to be used multiple times. We will probably run into that. I'm not exactly searching that out right now, so let me just go ahead and look at some more examples. Let's look at the limit as x approaches 1 of an x to the 9th minus 1 over an x to the 5th minus 1. Again, with this one, you always have to do this anytime you're thinking about using L'Hopital. When I plug in the 1, notice I get the 0 over 0 again. All right, that means L'Hopital can be used. Okay, with this one, is there some really fancy algebra that I could pull off and make that happen? Yeah, there's some algebra that could be done. Wouldn't be pleasant, wouldn't be quick, wouldn't be easy, but it exists. Since it's not quick and easy, I'm just going to go ahead and do it the quick and easy way. Bring down the 9. This becomes an x, 9x to the 8th once you take the derivative. Bring down the 5. This becomes a 5x to the 4th. All right. Again, notice that if I was to plug in the 1 right now, I do not get 0 over 0. I do not get infinity over infinity. That means you cannot use L'Hopital's again. Okay? Can't do it. You could algebraically simplify, and that's usually a good idea. Not always mandatory, but usually a good idea. This time it's definitely not mandatory. This algebraic simplification is not actually required, but it certainly doesn't hurt either, just to get a little bit of practice. Plugging in the 1 now gives me a 9/5. Notice plugging in the 1 back here would have given me a 9/5. And that's why I say the algebra wasn't mandatory, but it wasn't a bad idea either. Notice I didn't put an H here, didn't put an H here. It's because I didn't use L'Hopital's again. I didn't use it because I wasn't allowed to. Putting in this 1 doesn't give you a 0 over 0, doesn't give you an infinity over infinity, so no L'Hopital allowed. All right, so let's look at limit of e to the x minus 1 over x cubed as x approaches 0. The limits that I've been doing so far all seem like there were limits as x approached 1. I want you to see that that's not the only thing you'll be working with, not the only thing at all. Right now, if you plug in a 0, notice you get e to the 0 minus 1 over 0 cubed, and that is a 0 over 0 scenario. So once again, L'Hopital is allowed. Okay, so this is going to be equal to, by L'Hopital's rule, limit as x approaches 0. Derivative of e to the x is e to the x. Derivative of 1 is a 0, so it goes away. Derivative of x cubed is a 3x squared. All right. You thinking about using L'Hopital again? Well, let's check and see if we can. When I plug into the 0, I get an e to the 0. When I plug in the 0 here, I get a 0. E to the 0 is 1, over 0 is 0. Okay, take a look at that. What I have is a 1 over 0, and that, just to state the obvious, is not 0 over 0. All right, that is not an infinity over an infinity. So that is not an indeterminate form. I cannot use L'Hopital's rule. Okay, you will come to find, if you haven't noticed already, that whenever you plug and chug, like I've been saying, and end up with a constant on top that's a non-zero constant with a 0 on the bottom, with situations like that, you cannot use L'Hopital's rule. All right, this is not an indeterminate form. A non-zero value on top of a 0 like that, what that means is that that limit is heading towards one of the infinities. A non-zero value on top of a 0 means there's an infinity involved here. All right, now since we're approaching 0, okay, since we're approaching 0, and e to the x is always positive, all right, what's happening here, and what you could do, actually not a bad idea, just occurred to me. What you could do is you could look at that graph, and that would shed some light on what's happening. If you look at e to the x minus 1 over x cubed, if you look at that graph, what you'll notice is that when you head towards 0 from either side, it's strictly positive. I mean, it's strictly positive on both sides. All right. So what it turns out that implies is this is a positive infinity. All right. So again, a constant, a non-zero value on top of a 0 means you're heading towards one of your infinities. All right. And again, can L'Hopital's rule be used more than once? That question kind of came up. Let's see if I can find one. Let's look at the limit as x approaches infinity of e to the x over x cubed. All right. With this one, if you plug and chug, e to the x, again, if you think about what that graph looks like, that's a increasing function. It's a exponentially increasing function. X cubed is an increasing function, especially over there on the positive side. So if I plug and chug the infinity in here, you'll get infinity over infinity. Right? That means L'Hopital can be used. Taking the derivative of e to the x, I get e to the x. taking the derivative of x cubed, I get a 3x squared. All right, oh, hold on. Totally ran off and forgot my limit notation. This is the limit. X approaches infinity, and then e to the x over 3x squared. Once again, if you plug in the infinity, you get an infinity over an infinity. So once again, I can use L'Hopital's rule. Since the indeterminate form, after applying L'Hopital's rule, stayed indeterminate form, I get to use it again. All right? And once again, if I plug and chug, I get an infinity over an infinity. So once again, that means I can use L'Hopital's rule. And this time when I plug and chug, I get infinity over 6. All right, once again, that is not on the list of indeterminate forms. So therefore, we should know what it is. That one's an infinity. If you take an infinitively large value and divide it by 6, you still have an infinitely large number. Now, on occasion, you're going to get problems where you hit one of your indeterminate forms and it's not in a 0 over 0, or it's not in a infinity over infinity type format. Okay, so with those, what do you do? Well, the answer is you do some algebra. You actually have to do, on occasion, you have to do quite a bit of algebra. So, for example, let me see if I can find something worthy of what we're talking about here. All right. Let's see. Oh, this one might work. What if I had, hard to find good examples sometimes. The limit as x approaches 1 of x over x minus 1 over natural log of x. All right. Let's see what happens if we were to plug and chug. Let's see what would happen if we were to plug and chug. If I just plug in the 1, I get a 1 over a 0 minus a 1 over a 0. All right. That implies that there is some sort of infinity minus infinity here. All right. Now, if it's an infinity minus a negative infinity, that's not an indeterminate. Infinity minus infinity are the only indeterminates. So again, maybe a little bit of graphical help is in order. If I look at x over x minus 1 and take a look at what that's doing as you head towards 1. All right. Well, as you head towards 1, from one direction, it's heading up to infinity. All right. From the other direction, it's heading down towards negative infinity. All right? So let's look at this as a right hand versus left hand interpretation. As you approach 1 from the right, this one's going up to infinity. So from the right hand side, I have an infinity minus, now let's look at the other one. Let's turn that graph off for a second. Now let's look at 1 over natural log of x. With that one, as you head towards 1, it's heading up towards infinity. All right, so as you head towards 1 from the right, it's an infinity minus an infinity. Now let's go and look and see what happens as you come in from the left. With this first graph, as you head in from the left, it's heading down to negative infinity. Okay, and with this other graph, as you head towards 1, from the left, it's heading down to negative infinity. All right, so this one becomes minus a negative infinity. All right, so 2 negatives make a positive, and flip it around. All right, so basically what that means is that no matter which direction you're coming from, you have an infinity minus infinity scenario. That makes it an indeterminate form of L'Hopital. Right? And again, you have to be very meticulous in the verification, or you'll use L'Hopital
We're not supposed to use L'Hopital. All right, so can I go ahead and just take derivatives? No, I do not have it in a single fraction. So what I'll need to do is get a common denominator. I'm going to have to put these together into a single fraction. So here, I'll multiply by natural log of x, both top and bottom. Here, I'll multiply by an x minus 1, both top and bottom. And I will get natural log of x minus an x minus 1 over natural log of x times x minus 1. And again, with me running off and forgetting my limit notation. All right. Cleaning up the numerator just a little bit. This is natural log of x minus an x plus a 1 over natural log of x times x minus 1. And one more time, I forget my limit notation. All right. Now, if I plug in a 1 right now, let's see what happens. Plugging in a 1 right here, I get a 0. This is a negative 1 plus 1, so that's a 0. Plugging in a 1 right here, I get a 0 times a 0. So what happens, and what will happen almost without exception, is that once you do your algebraic simplification, if you have one indeterminate form, it'll turn into a different one, but it will still be an indeterminate form. And this is one I can use. This is now useful because now I can take my derivatives. I can actually apply L'Hopital. So this will be equal to, by L'Hopital, the limit as x approaches 1 of a 1 over an x minus a 1. That's what I get on top. On the bottom, I'm going to have to use a product rule. First times derivative of second, okay, plus second times derivative of first. All right, and doing a little bit of algebraic simplification. This is the limit as x approaches 1, 1 over x minus 1. This is a natural log of an x. This x right here, when you multiply, will cancel. And then you got a minus 1 over x right there. All right. So again, I have an h here because I applied L'Hopitals. Don't have an h here because this was just algebraic cleaning. All right. When I plug in the 1, let's try that again. I get a 1 minus 1, which is a 0 on top. This is a 0. This is a 1 minus 1 on the bottom. I get 0 over 0 again, which is not the end of the world. This means I'm still allowed to use L'Hopital. All right, so I'm going to go back, and I'm going to hit it with L'Hopital one more time. This is the limit as x approaches 1 of, treating this as an x to the negative 1 power, it becomes a negative 1 x squared. That goes away. This becomes a 1 over x. That goes away. And this is a negative 1 power. This is an x to the negative 1 power, so it becomes a negative 1 x to negative 2. All right, so this is the limit as x approaches 1 of negative x squared over negative negative make a positive, and this is a 1 over x plus 1 over an x squared. Well, this time, if I was to plug in a 1, let's see what I get. This becomes a negative 1 on top and a 1 plus 1 on the bottom. And then that's it. There's no equal to. That's it. That's the end of it. All right. So again, with that one, you see that L'Hopital's rule could be applied more than one time. And as a result of that, we eventually got something down to where we could algebraically simplify it and go from there. All right. So with that one, we were able to use L'Hopital in a lot of algebra. With others, you'll have to use more creative means. Let me show you one more example. What if I had the limit as x approached infinity of x to the 1 over x? So we'll look at a classic example there. All right. So when I plug in the infinity, let's see what I get. I get an infinity here. 1 over infinity is 0. And is that on my list? Absolutely is. That is one of my indeterminate forms. All right, so what am I going to do? Well, I'll use L'Hopital, but I have to do a little bit of algebra first. In this one, you have to be a little bit more creative. I'm going to let y equal x to the 1 over x power. I need to do some manipulation like this, of this part. All right, I have a 1 over x up here that's not convenient. So I'm going to take the natural log of both sides. Actually, natural log of y would equal natural log of x to the 1 over x. With this natural log taken, this 1 over x can come down, and this can be written as natural log of x over x. All right, now, if I take the limit as x approaches infinity on this, you notice that a L'Hopital is needed. All right, so if I take the limit as x approaches infinity, natural log of x over x, a L'Hopital can be used, so I'll use it. This becomes the limit as x approaches infinity of 1 over x over 1, and that turns out to be a 0. All right, so this limit is a 0. All right, but this is what natural log of y looks like. This is the limit as x approaches infinity of natural log of y. That's what equals 0. Okay, and y is the expression that I want the limit of. So to reverse this process, I use the inverse to the natural log and I apply an e. So in other words, the answer to this problem, since I took a natural log and then took the limit, the answer to this problem is e to the limit value that you got. So that one turns out to be a 1. Right? And a lot of these limits, I don't know about all, can be verified with a little bit of calculator help. I've been showing you some graphs. Let's look at a table. Let's look at x to the power 1 over x. I'm trying to take the limit of this as x approaches infinity. So I'm going to go to a table. And I'll put in, I'll start with a 1. And you get a 1 from that. Put in a 10. Put in a 100. Put in 1,000. Put in 10,000. Put in a 1 followed by as many zeros as you feel like typing, and you see that at some point the calculator can't tell the difference between that and 1, and that makes me feel a whole lot better that my limit was worked out correctly. All right, so again, with a little bit of algebraic manipulation, these limits can be found along with the help of L'Hopital's rule.